Welcome back. In the second part of this unit, we're going to get completely away from those differential equations, slope fields, all that stuff. And we're going to start exploring what we have when we have graphs that enclose an area. We want to find the area of the graph, area enclosed between the two graphs. We're going to spin it around different axes and form solids of revolution. We're going to find the volumes of the solids of revolution. I'm not going to do a whole lot of integrating by hand in this part of the unit at all. I'll just show it how you would set it up, and then you can put it in your calculator or integrate it yourself. If you have questions about how you integrate it, please let me know. In this first one, what's going to happen is we're going to find the area between curves. So if we have a couple of different functions and we get different boundaries, we can find the area that's bound by the graph by taking the integral from a to b of f of x minus g of x, where f is going to be larger than g. These could switch, or you might have more than one set of equations that you have to deal with. Sometimes the boundaries are vertical lines or horizontal lines. Sometimes we might have it in terms of x, or we might have it in terms of y. I'll do an example of that a little bit later on. If you don't have a sketch, get a sketch. A good sketch is $1 million. And then determine whether you're going to integrate in terms of x or you're going to terms in y. Determine which one is larger. I'll show you kind of some tricks on that. And then find the lower and upper limit, set up your integral, and then solve it. So in my equations, my first one, what I have is I have this top equation. I'm looking for the area of this region in here. This top equation right there is my g of x equation. That's the 4 minus 6x minus x squared. This is my 2x squared plus 5x. And in doing so, I gave you a nice picture. I found that it intersected at -4 and +3. Those are going to be my limits. If you don't know that, you can set f of x equal to g of x to find those limits in this particular case. And you can obviously factor it to solve it, that kind of stuff. Now, if I'm looking on this interval, which one is larger? I'm not really sure because I don't have a picture of it. I can try a test value, so say 0. So if I plug in 0 here, I'm going to get 0. If I plug in 0 here, I get 4. So g of x is going to be larger. So I'm going to set up my integral. It's going to go from -4 over to +1/3, and it's simply going to be g of x minus f of x. If you have those in your calculator to graph it, you can just pull it back as y1 and y2. If you have trouble with that in the integration part of it or putting it in your calculator, please ask in class and I'll clarify for you. This one's a little bit trickier because we have these two different regions right here. They intersect at 4. That's an x value of -3. Excuse me, x value of 3, and that's an x value of 5. And it gets a little bit trickier because they switch which one's on top. So I can do one of two things. I can either write two different integrals, like the integral from 3 to 4. This part's going to be the cubic graph, which is my g of x on top minus my f of x. And then another integral from 4 to 5, and this is going to be f of x on top minus g of x. I can do it that way. Or because of the symmetry, I could just double one of these. It doesn't matter which way you do it. I'm going to do it the old-fashioned way. I'm going to write two integrals. So from 3 to 4, we have the cubic on top, so it's going to be g of x minus f of x dx. And then I'm going to add to that the integral from 4 to 5. But now I'm going to have the line on top, which is going to be f of x minus g of x dx. Sometimes the graphs won't necessarily intersect. In this particular case, I have an e graph, 3e to the x, and then I have a vertical line, excuse me, a horizontal line at -2. This graph, that e graph, would never intersect with -2. And so then they give me boundaries between 0 and 1, and those become my limits. So I'm just looking for this area right here. And it's going to be the integral from 0 to 1, and then the f of x graph is going to be on top. So the integral from 0 to 1 of f of x minus g of x dx, something like that. And then finally, the last one. This one gets a little bit more challenging because of this graph, y squared minus 1 right there. It gets a little bit more challenging. Because of this y squared, I want to integrate in terms of y instead of in terms of x. And then the second thing about that is that my limits have to be y values. If I'm going to integrate in terms of y, I've got to get y values. This equation is in the wrong format. I've got to write this as x equals y plus 1 because I need it in terms of y. So in this particular equation, I'm going to have to write out the equations because I don't have them in terms of f of y and g of y. So they intersect at -1. They intersect up at +2. And then the one that's going to be larger is the one that is further to the right. So it's going to be this line that's further over. So the y plus 1 goes first. So it's going to be y plus 1 minus y squared minus 1 dy. When you come to class, I'll take a look at these y graphs especially a little bit more, make sure you have an understanding of how to sketch those. That gets a little bit tricky every once in a while. All right, not too bad. We'll see you in class soon.